You'd think that math, started as a way to describe the real world, things like measuring land or tracking the planets or handling money. But it turns out to really get a handle on reality, we had to invent something that sounds completely fake, a new kind of number, a number that we literally call imaginary. So, yeah, let's get into this absolutely wild story. I mean, just listen to this quote from the physicist Freeman Dyson. It really gets to the heart of the whole thing. How on earth could something we totally made up, something we named imaginary, be more fundamental to how nature works than the real numbers we use every single day? It's an amazing paradox, isn't it? So that's really the big question we're tackling here. We're going to dive into this historical and scientific mystery and see how a huge leap of pure imagination gave us one of our deepest insights into how the cosmos actually works. To get started, we've got to go way, way back in time. For the early mathematicians, math was something you could touch. It was all about geometry. An equation wasn't just a bunch of symbols on a page, it was an actual physical shape. And this way of thinking, it created a huge mental block when it came to solving certain kinds of problems. This is just fascinating. Look at how they solved an equation like x squared plus 26x equals 27 without our modern formulas. They literally built it. They saw x squared as an actual square. Then, as you can see, they'd take that rectangle of 26x, split it right down the middle, and arrange the two new pieces on the sides of the square. To, well, complete the bigger square, they just had to add that final little corner piece. This meant they could physically see the solution. It's totally brilliant, but it also shows you just how locked in they were to thinking about math in terms of tangible shapes. And right here is where they hit a wall. Because if you think geometrically, negative numbers make absolutely no sense. I mean, what is a square with a side length of negative 27? Or what's a negative area? It's just nonsense. They went so far as to write up different versions of the same equation just to make sure they never had to deal with a negative number. So you can imagine, when they got to the much trickier cubic equation, a guy named Luca Pacioli, who was Leonardo da Vinci's math teacher, by the way, just declared a general solution was flat out impossible. But then, the Renaissance happened. And with it comes one of the most dramatic, soap opera-worthy stories in the entire history of science. The solution to that impossible cubic equation wasn't found in some quiet library. No, it was forged in the fire of a high-stakes intellectual battle in 16th century Italy. Okay, so the whole thing was about secrets. Around 1510, a mathematician named Scipione del Ferro cracks the code, but he tells nobody. He wanted to keep it as a secret weapon for these public math duels they used to have. Right before he dies, he passes the secret to his student, Fior. And what does Fior do? He foolishly challenges a self-taught genius named Niccolo Tartaglia. Big mistake. Tartaglia, under pressure, figures out the secret for himself and wins. This gets the attention of this other brilliant guy, Girolamo Cardano, who manages to coax the secret out of Tartaglia and then turns around and publishes it for the whole world to see a few years later. And this wasn't just some casual promise. This here is the actual solemn oath that Cardano swore to Tartaglia. He promised not only to never publish it, but to write it down in code so nobody could understand it after he died. That's how incredibly valuable this secret was. Of course, he found a loophole and published it anyway. The drama. So Cardano's book, Ars Magna, it was a total masterpiece. It had the complete solution to the cubic equation. But there was a glitch, a kind of ghost in the machine. Sometimes the formula would be working its way toward a perfectly normal, real-world answer, but to get there, it would spit out these bizarre, seemingly impossible numbers. All right, let's look at the specific problem that basically broke math for a while. The equation is x cubed equals 15x plus 4. It looks simple enough, right? And it is. You don't even need some fancy formula for this. If you just guess and check for a minute, you can see that x equals 4 is a solution. 4 cubed is 64, and 15 times 4 is 60, plus 4 is also 64. It works. A nice, simple, whole, real number. But when Cardano plugged these numbers into his shiny new formula, this is what it spit out. Just look at that thing. To get to the simple, obvious answer of 4, the formula was telling him he had to calculate the square root of negative 121. Back then, that was pure mathematical heresy. The square root of a negative number was the official sign that there was no solution. And yet here was a problem that definitely, clearly had one. You know, even the great Cardano was totally baffled. He couldn't make this fit with his geometric view of the world. For him, it meant dealing with negative area, which was just absurd. So
He just dismissed the whole problem, called it as subtle as it is useless, and basically just gave up on it. And for about a decade, that's where things just sat. The problem was just stuck. Until an Italian engineer named Raphael Bombelli came along. And instead of trying to avoid this paradox, Bombelli decided to stare it right in the face. He took a massive leap of faith.
So Bombelli's idea was both radical and simple. He basically said, hey, what if we just stop freaking out about this? What if the square root of a negative number isn't impossible? What if we just decide to treat it like a brand new kind of number, give it its own rules, and just see where it takes us? He decided to just play with the symbols and follow the logic, even if it didn't seem to connect to the real physical world.
And what happened next was just incredible. So Bombelli figured out that those two bizarre terms from Cardano's formula were actually just different forms of 2 plus the square root of -1 and 2 minus the square root of -1. So when the formula said to add them together, something amazing happened. The imaginary parts, the plus square root of -1 and the minus square root of -1, poof, they just canceled each other out completely. And what was he left with? 2 plus 2, which is 4. The right answer. It was like actual magic. You had to go through this strange imaginary world to get back to a real solution. Now, this breakthrough was huge. It basically freed algebra from the shackles of geometry. But for hundreds of years, these imaginary numbers were still just seen as a weird mathematical party trick. It wasn't until much, much later that we finally understood what they really are, which solves the big mystery we started with. The big aha moment is realizing that imaginary numbers aren't just an idea, they have a direction. So if you picture all the real numbers on a line going left and right, the imaginary numbers live on their own line going up and down, perfectly perpendicular to the first one. And together, they create this amazing two-dimensional space for numbers called the complex plane. And this is the real magic trick. Multiplying by I isn't just making a number bigger or smaller. It's an operation. It's a rotation. So let's follow along. You start at the number 1, you multiply by I, and you rotate 90 degrees up to I on that vertical axis. Multiply by I again, another 90-degree turn, and you land on -1. That's why I squared is -1. It's not magic, it's just a 180-degree turn from 1. Do it again, you rotate down to -I, and one last time brings you right back home to 1. It's that simple. Multiplying by I just means rotate 90 degrees. So why does any of this matter? Well, because rotation is the basic language of anything that goes in cycles or oscillates. In other words, waves. The function e to the ix perfectly captures this rotating behavior, and it lets you describe both sine and cosine waves in one beautiful, compact package. And that, it turns out, is exactly the tool that physicists needed to describe the totally bizarre wave-like nature of reality down at the quantum level. Which brings us right back to Freeman-Dyson. The physicist Euler and Schrödinger put I, the square root of -1, into his big equation for quantum mechanics. And just like Dyson said, suddenly it made sense. This weird number, born from a dramatic math duel in the Renaissance, became the key to understanding the behavior of every single atom in the universe. It's the foundation for pretty much all of modern chemistry and physics. And that, I think, is the coolest takeaway from all of this. The story of imaginary numbers shows us something really profound about how we learn things. By being brave enough to let go of a model of reality that seemed so concrete, so tangible, that world of physical shapes, mathematicians found a more powerful, a more complete, and ultimately a much deeper truth about how the universe really works. It just makes you wonder, what else could we discover if we were brave enough to question the things that seem real today?